Okay, thanks. Okay, hi. Hi, Greg.
Good morning, Candace.
How are you?
I'm well, thank you.
So people who don't know you, I feel like a lot of people on the call actually do know you and probably have worked with you, but can you tell us a little bit about what you do at RBR?
Chief cook and bottle washer. I end up, what did I do? Most recent exciting thing I did for the company was varnish the calibration tables.
Ooh.
And occasionally I do some product design and various, and a little bit of sales.
Okay, cool, awesome. So I will let you take over. And like I said, folks, ask your questions in the chat window. And over to you, Greg. Thank you.
Okay, thanks, Candace. Thanks, everybody, for coming. Nice to have you. I thought no tour of the calibration lab and the extremes of temperature there would be complete without showing you a little bit about what the weather's like in Ottawa. And so if all you can see is white, that's correct. We're just having our second snowfall of the season right now. I guess we've had about 30 centimeters in the last day or so. Welcome to RBR. This is our front entrance, and I'll walk you from here through to the calibration lab. As Candace mentioned, we've just been here for about 2, maybe just coming up on 3 months now. We haven't moved very far. We moved about 500 meters from our old building, and we moved because we needed more space. So we've doubled the amount of space we have in this building. You will find that the calibration lab probably doesn't have so many people in it. It's lunchtime right at the moment here in Ottawa. And so as we walk through, we might find a few people passing me on the way to the lunchroom. In addition, we're coming up on the last month of the year, and it's a good time for people to get their last holidays done. So we're just walking through and on our way to the calibration lab. It involves passing by the production floor on the way, but we won't stop. And yes, it looks like we have only 3 folks in calibration at the moment. So we're going to talk a little bit today about really the 3 major calibrations that we do by volume, by number of them in a year, which are temperature, pressure, and then conductivity. And then probably we'll have a look at what else is going on, perhaps talk about oxygen a little bit as well. So we'll start off with temperature. We have a range of instruments, and of course the CTD is very common, but actually more common in terms of volume is the single channel RBR solos and the dual channel RBR solos and duets. I have one here that I've just lifted up. These are our compact logger family. This one's not yet labeled as it's in the cal lab, and it's just been undergoing pressure and temperature calibration. How do we do that calibration? Well, we put them into baths like these ones in this section. So these are small water baths, which are filled with a slightly alarming looker green water. That's water mixed with methanol in there. And that's because we calibrate from -5 to 35 degrees Celsius, and we don't want that fresh water to freeze. In fact, we have a bath that we also will take down to -40 when we're doing extended calibration. So although our standard range is -5 to 35, we'll do extended temperature calibrations up to about +50, down to -40. And those differ according to your requirements. We wouldn't typically recommend that battery-powered instruments go to more than +50. The batteries don't like it very much. So these baths will have set points on them. For instance, looking at a bath here, it says it's at -0.56 degrees. the one adjacent is at 9.37. But we don't actually trust those temperatures. Those temperatures are just indicative, and the actual temperature in the bath might be different by ½ degree or so. What is special about these baths is that they're very stable. And so regardless of whether it's -½ degree or -1 degree, it's that the volume of liquid in there is all at the same temperature to within a millidegree. That means that every instrument that is put into them for calibration will see exactly the same temperature. But we can't use that indicator on the front to calibrate them because it's wrong, and we don't actually care that it's wrong because we never use it. What we do instead is we use a platinum resistance thermometer to calibrate these, and so the instruments are deployed in these tanks alongside the platinum resistance thermometer, and the SPRT, standardized platinum resistance thermometer, is read out by a so-called super thermometer. So I have some SPRTs which are sitting out at the moment, just to show you what one looks like. Get rid of the close peg on that one. So this is an SPRT, and the part that is closest to the camera, see if I can hold this steady, probably not. You probably excuse my motion. It's just before lunch and I'm probably slightly hypoglycemic. That tip is a coil of platinum that has been wound. Let me see if I can do that from here, right here. And platinum has a very uniform characteristic with its resistance being proportional to temperature in an equation known as the Steinhart-Hart equation, which involves the logarithm of a cubic. It's really straightforward. And so what we need to do is to measure the resistance of that. Now, the reason for that being in a long tube is that we want the temperature at the bottom when the SPRT is inserted, like this one has been, into the tank, not to be contaminated by any of the heat that is up near the handle. And so within the SPRT itself are a series of baffles, which you may or may not be able to see close to my fingers. Those baffles prevent the heat from flowing down. To measure that, it's done in a resistance bridge. We have one here that I'll show you. This is a 4-channel so-called super thermometer resistance bridge. And these numbers are rotating through as each channel is being cycled. It takes about a second to make a measurement. And you can see that we're measuring to about 10 microdegrees. Our accuracy of the SPRTs, uncertainty is about 0.1 millik. Question then arises, okay, so you can calibrate against your SPRTs, and that's all well and good, but how do you know that the SPRTs are accurate? And we calibrate those against primary standards. Primary standards are physical artifacts where their intrinsic properties are those that we're going to use as temperature set points. And in fact, temperature scales, such as the ITS 90, which is behind me on the wall here, are defined by those primary standards. So the temperatures of the ITS 90, the primary standards range from -259 up to about just under 1,000 degrees. Just under 1,000 degrees in Celsius. But for oceanographic work, we're obviously interested in temperatures somewhere around, let's say, the lower third of that scale. And so if we look there, we can see that there is 3 physical artifacts that are interesting to us. The most important is the triple point of water. The second is the melting point of gallium, which is the kind of fun metal that if you ever get, it's solid on the table and you pick it up and hold it in your hand and it melts. And the third is mercury in the triple point, and I wouldn't advise ever picking that up unless you want to become mad as a hatter. The triple point, in case you're not familiar with it, is the state at which a material takes on it's in equilibrium, and it takes on both or all three of solid, liquid, and gaseous phases at once. And I have here a triple point cell of water. So this is a closed glass cell, and it has been filled with about 3/4 of the way up with ultra pure water, something like 99.9999% H2O and nothing but. Above it, all the gas was evacuated, and so the only thing in there now is water molecules in vapor form. And those of you who are sharp-eyed will notice that this one's a broken one, and that's because I only let myself hold the broken ones on camera. I don't want to, they do get damaged occasionally. This one has some contamination that's leached in over the years. So this is a demo one. Obviously, you can see that this water is not at its triple point because we only have the liquid phase and the solid phase. But if down this central cylinder, which extends almost to the bottom of the cell, we were to put something quite cold, like dry ice or a solid carbon dioxide, we can freeze a mantle of water around this cell. Igor, would it be possible for you to come and show me the triple point cell again? So I've asked one of our staff to come and open one of the tanks where we're maintaining the triple point cells at the moment. So you see, Igor is lifting up by the same handle. Here, a triple point cell, and inside, I hope you can see this on camera, it's actually frozen. It looks like it's frozen all the way to the edges, and that would be petrifying because you will explode the glass. But it's an optical effect because of the index of refraction and the curve of the glass. And so what we have in here is the water in its liquid phase, its gaseous phase, and its solid phase all at once. And they're actually very well combined. So if Igor rotates it quickly, you will see that mantle of ice is not actually physically glued to the walls. It's lubricated by a thin layer of water. Okay, thank you very much. Okay. At its triple point, pure water has a temperature of, as you saw on the screen, on the 0.01000 degrees Celsius. And so we use that as a reference in which to calibrate the SBRTs. Now, we also saw gallium, the melting point, and the triple point of mercury up there. And we have those cells as well. So we have a gallium cell here in metal and mercury in the other one. So about, I don't know, probably once a week or so, we check all the SBRTs against the primary standards, and then we do full calibration slightly less frequently than that. We exercise the instruments across a range of temperatures, as I said, -5 to 35, and we do so in 5-degree steps. All of the data that comes from these instruments, and here are 3 instruments that are still in the bath at the moment, all of that data goes into a database that then is used to align the electronic values that come out of the instruments with the precise values that we've measured using the super thermometers. Most of the tanks are empty at this time of day because we perform all of the calibrations overnight. We can set up the instruments, load them into carousels, and then drop them in. I can find, for instance, under here, a calibration carousel. This will hold 20 of our compact instruments, and we lower that into the tank, press a button, and come back in the morning to retrieve the instruments. For pressure, which is by volume, the second most common calibration that we do here, we do that not by attaching hoses to the instruments just to calibrate the pressure sensor, but we also perform a leak test at the same time. And so we do that by immersing the instruments completely in these small tanks. They can be taken up to 2,000 meters in these tanks. And we actually have two of them because we calibrate every instrument twice. We calibrate it once at room temperature in this tank, and then we calibrate it a second time at about 2 degrees Celsius in the second tank that has the insulation and the chiller attached, as you can see. The pressure is applied pneumatically through a gas, not through liquid hydraulically. And so these nitrogen tanks that are here in the corner are being driven by these pressure controllers. We don't actually fill the tank with gas because we don't want to store a lot of compressed energy. That's called building a bomb, and we don't like to do that inside the lab. Instead, we fill the tank with water, put the instrument inside, and then pressurize only the very top of the fluid using the gas-filled pipes. The advantage of using gas is that it's very easy to control and modulate. And so with these controllers, we're able to hold, again, the same kind of principle of multiple set points from 0 to full scale. You can see that this controller is currently at 10 dbar, which is to say it's open, and that reflects this tank over here. The tank that is hooked up at the moment is controlled by this one, and you can see it's holding 535 dbar at the moment. If you subtract atmosphere from that, that's 435 meters of water column. These tanks, as I said, can go down to 2,000 meters, but sometimes we want to go deeper than that. And the depth of the Pacific is just over 10 to 11 kilometers. And so we have a high pressure tank as well. That's this one here. And this one will go, there we go, if I can do that. This one will go to the bottom of the Marianas Trench, if you like. This one is compressed, pressurized hydraulically. So all of these actuators and valves on the outside are used to drive in pressure and release it. And likewise, we have an insulated jacket and a chiller, which keeps it cold, because for deep water calibration, we particularly want to verify the performance at oceanographic temperatures, kind of 2 degrees when you're down at the bottom. I'm going to walk over to the conductivity area. And I'm going to ask Igor, who helped with the SBRTs a moment ago, to tell us a little bit about this conductivity area and what we're actually looking at in terms of the tanks. Good morning, Igor. Good to see you again.
So it's day already. So we're in a conductivity calibration sector, and I'm just running ultrasound measuring salinity samples taken from the morning check in our conductivity bus. So we have two big volume conductivity bus, one set to 15 degrees and 35 salinity, practical salinity. And second bus set to 24, 25 degrees and 35 salinity. So one is bus controlled by external thermal bus set to 13 degrees 0.5, but after all heat loss, get to 15 degrees in the bus very accurately.
The tank's got two lids, Igor. Why does it have two lids?
Yeah, so it has internal contour to keep temperature around the
that's the copper pipe that we can see inside there.
Yeah, with heat exchanger. So internal volume of salt water has not any metal parts, not any other heat exchangers which could affect.
So it stays nice and clean.
So yeah, it's nice and thermally uniform. So for now you can see one of our legato deployed for calibration. So it's handled in the middle, and we performing measurements of conductivity and temperature in the bath.
And the second one doesn't seem to have a double jacket.
Yeah, so it's set to balance with room temperature, with only having internal submersible pump heat and just eventual balance with room temperature.
So what's the temperature in our lab here?
So now it's 22.5 degrees.
All right.
It's make about 24 degrees in that part.
So that submersible pump that's using to
Yeah.
stir the water
Yeah.
adds a couple of degrees, which is why we're sitting closer to
Yeah,
25.
the same with the same.
Right. 13 degree set point, 15 degrees actual.
Yeah, and we set our outer south solenometer reference to 24 degrees. So when we measure temperature in 24 degrees past, we measure at the same temperature. And
Okay.
15 degrees, it's our calibration actually, normal temperature of calibration for conductivity to keep it well aligned with practical salinity scale reference temperature, 50 degrees too.
Yeah.
So we, in all our measurements of conductivity, we keep temperature 15 degrees as defined by practical salinity scale.
Great.
Some other area with linearity test,
Yeah.
if you're interested in that part.
So usually before
We
the
set
conductivity calibration occurs, we prove to ourselves that the conductivity cell is linear. And it's one of the questions that occurred in the earlier webinar was whether you can use our conductivity cell in fresh water. You absolutely can, because the inductive technology is linear over the full range. We prove that as it's part of the design, but we prove it as part of the calibration process. And that allows us then to work through these two very simple tank immersions that are done. In electrode-based conductivity, typically that's done by taking a bath of salt water and varying its temperature over a wide range. We don't need to do that here. We can keep those two tanks at constant temperature with much lower energy input. Thanks very much, Igor. I'm going to walk over to oxygen and see, I think we may or may not have an instrument in oxygen calibration at the moment. Introduce you to Tekai. Good morning, Tekai.
Morning, Greg.
So what are you doing here today?
So right now I don't have anything in there, but
Okay.
by default we have a reference optode in there just to make sure that everything in the lab is as it should be. It's also a slow, so
Yep.
that's just a resident,
Yep.
permanently stays in there. It's distilled water, so it's air saturated water that we use, and that's just a bubbler to get the water.
Like from an aquarium, really?
Yes, really,
Yep.
yeah. And there's a stirrer in there to keep things going. This is where we do our last audio checks before the instruments get shipped.
So this isn't really the calibration, it's more the quality check.
Yes, it is.
And so
Yes.
here we're just doing a quality check at 100% saturation.
Yes.
Do we ever do 0%?
We do zeros, but not for our optodes.
Okay.
So because of the foils on
Yep.
our optodes, we don't do zero saturation for them. But
Okay.
for oxyguards and Anderas, we do zeros.
Yep.
And zeros get done with sodium sulfide.
Okay, which basically
Saturated,
eats
which
up the
eats
oxygen molecules in the
Yes,
water.
Yes.
Right.
And that's when we do our zeros.
Okay.
Yeah.
So how do we do an optode calibration? We don't use just a bucket.
No, we don't use a bucket. So over here, we have a bath. It's a huge bath filled with distilled water again.
Okay.
In there, we have two pumps to keep things circulating. We have these cables in there that end up pumping the gas in there. We have bubblers at the tip to spread it in. And we have cooling points
Okay.
in there too.
So the coil must be for this chiller.
Yes, it is. So this is a temperature controlled bath. It's computer controlled, so we don't have to be pressing things when we're here.
Yeah.
And we end up doing temperature ranges from minus 1.5 all the way to 35.
Plus 1.5.
Plus
to
1.5,
35.
not
Yes.
one, not minus.
We
plus
want to get
1.5.
close to zero, but
Close
not
to
quite
zero,
freezing.
but not zero. We don't want to freeze the tank.
Right.
Yeah.
And what goes through those gas pipes?
Gas pipes, we have nitrogen and oxygen from these gas bottles here. So these gas bottles, tubing everywhere, connected to these MFCs, mass flow controllers, that are controlled all the way over here.
Okay.
Programmed so that no one is pressing buttons in here, and we set them up to do the gas mixes for the runs.
So if we do temperature from 1 to 30 to 35 degrees, how many points of temperature do we use?
We end up using seven.
Seven?
Seven
Okay.
temperature points.
And the MFCs, the mass flow controllers, allow us to change the blend of oxygen and nitrogen.
Yes, they do.
How many plateaus of oxygen do we use?
We use 6.
Okay.
Zero where there's nothing really, just
Yeah.
nitrogen bubbling, and then 25% oxygen, 50% oxygen, 75 oxygen, 100 oxygen, 125
Okay.
oxygen saturation.
Okay. So
Yeah.
almost 49 points
Almost
that we
49
calibrate
points.
over.
Yes.
And then that surface that we generate is what we fit the polynomial to.
Yes.
Those coefficients then get stored.
They get stored into the sensor, and then off they go.
Off they go.
Yeah.
Lovely. Thank you very much.
Thank you, Greg.
I didn't really ask TechEye to explain, but although she mentioned having reference optodes, our oxygen calibration is typically done against transfer standards. But just like with the super thermometers, we need to calibrate those transfer standards on occasion. And so we do that with Winkler titration. We have a small titrator here and scales, and that would be done once a week just to ensure that there's no drift. But once a year, we do a full Winkler over all 49 points, or 42, whatever it was. And that takes quite a long time to do, because a Winkler is a slow process for those of you who know it. So that's something that we do routinely to make sure that we have real traceable standards going back to the very beginning. I am going to wrap up, I think, at that point and walk out of here. But I would be happy to take any questions about calibration. Lots of things I didn't cover, but I wanted to give you just a brief overview of the way that we do things at RBR. Much quieter out here.
That was awesome, Greg. Thanks so much. I'm going to open it up to anyone who wants to come on video or on audio, or you can throw something in the chat if you don't want to do those things, to ask some questions. If not, I have some, but I'm going to let you guys ask your questions first.
Oh, come on. Let's hear one of yours.
Okay. So you have the 2 conductivity baths.
Yep.
Is every CT cell put in both baths, or do you just need to do it in one? Okay.
So we do that resistivity check first, which is a box that really contains a series of resistors, allows us to change the resistance from open circuit down to a low value, which is the same as changing conductance from 0 up to a high value. And that proves to us the linearity. And then we take every instrument and it goes into both baths, one after the other.
Awesome.
We also are taking into account the temperature calibration, which was done prior for the instrument, and also the pressure calibration, because the conductivity cell has a temperature dependence. It also has a pressure dependence. And so we want to correct those as well. I would call those compensating values as opposed to really calibrating values.
Awesome.
I can see that the questions chat is sitting ominously quiet. I can't believe I actually answered everybody's questions in the talk. I think I purposely left things out just to see if anybody was listening. It's funny how on a Zoom, the awkward silence when you're on a chat is maybe slightly less awkward. Good to see some of the familiar names here as well. Good morning, Thomas. Good afternoon, Thomas. Daryl. Oh, look at this. My goodness, now they're coming in like...
Thank you, guys. Yay.
Like buses. There are none for an hour, and then they all come in 5 minutes. Yes, so absolutely. Everybody can ask questions, and I will repeat them. So Daryl Adams asks, when sensors are returned for calibration, do they enter the same baths as you showed? Yes, they do. So our calibration process for recalibration is the same as it is for calibration in the first place. There are some sensors that can be calibrated in the field, and they don't need, for instance, the full 49 points of oxygen calibration. With an optode, it's important that you calibrate it yourself, and you can do so with a single point or 2 points, 0 and 100%. Temperature, pressure, and conductivity, we recommend should be calibrated every year in order to maintain the calibration accuracy. But sensors like turbidity can also be easily checked yourself. CTDs are a little bit harder. You require some of that specialized equipment to do it. One of the things I should say, Daryl, is that we really appreciate it if you clean your sensors before you send them back for recalibration. As you can tell, we want that water to remain spotless. And so if we have to spend a lot of time at the sink with a scrubbing brush to get various bits of your organic matter off, well, it makes the calibration guys a bit tetchy in the morning. So Blair Greenan asks, do I recall correctly that you store the calibration results internally in the sensor? If so, does it store various versions of the calibration history? Yes, Blair, you're correct. All of our sensors are able to produce calibrated output, and they do so because the calibration coefficients are stored internally, and the sensor is able to apply those coefficients with the calibration equation. For a thermistor, for instance, there are 4 coefficients, which are those coefficients of the cubic that I spoke about in the Steinhart-Hart. The Steinhart-Hart equation is implemented inside the instrument. It's also implemented in Ruskin, for instance. If you told the instrument to measure raw values, kind of voltage ratios, as we'd say, then the calibration coefficients can be applied afterwards, and you could apply different calibration coefficients. In fact, some people, especially those who are in a rush, deploy our instruments without a calibration and then send them back for calibration afterwards and apply them to the data they'd previously gathered. There are a couple of tricks involved in doing that, and so talk to us if that's your intention. We do not store inside the instrument all of the previous calibration episodes. However, those are stored in our database, so we can see the calibration history of every instrument that has been through here. We can see its original calibration when it was manufactured, and every subsequent recalibration that was done over the years. Karen asks, how often should RBR solos be calibrated? The most common RBR solo is a solo T, which measures temperature. Temperature, conductivity, and pressure we would recommend all being recalibrated once a year, regardless of which instrument they're on, whether it's a solo T, a duet TD, or a concerto CTD. However, that is to maintain the datasheet accuracy. And so if you're interested in the datasheet accuracy and using the instruments to their full potential, then that's essential. If, for instance, there are some engineering applications where instead of 2 milligrees of temperature, you might be interested in data that's good to 1/100th of a degree, you don't have the same requirement to calibrate every year, but you probably in an engineering application do have the requirement for a certificate of calibration. So in both cases, you should really talk to us about that. The drift of the temperature sensor, for instance, is only on the order of a couple of millidegrees per year. And so if I was going to be measuring water temperature to 1/10th of a degree, I wouldn't recalibrate this sensor ever. Within my lifetime, it won't drift out of that. But if you're doing proper oceanographic work, then yes, annual recalibration is a good idea. Let's see. Guangyu Zhu, pardon my pronunciation. Oh, Alex. Sorry, I skipped one. Oh, Alex. Okay, I think Alex. Yes, okay, right. I see your questions coming up. Okay, does RBR have a calibration facility in the US? No, it doesn't. We're based just across the border in Canada, about 150 kilometers north. And so our calibration is here in Ottawa. Unfortunately, in North America, the calibration facilities for CTDs, for instance, that used to be at national laboratories have migrated inside manufacturers. You can still get temperature and pressure done in some places, commercial labs, for instance, but other countries in the world, like NCOSM in Tianjin in China, or JAMSTEC in Japan, or Cesaro in Australia, NOC in the UK, Ifremer in France, they maintain national calibration labs, which are excellent, and our instruments can be calibrated there if that's convenient for you. We always work together with the calibration labs to make sure that they can get the best out of the instruments. From the US, it's straightforward to ship instruments to Canada, and the cross-border issues aren't really issues due to the North America Free Trade Act. James asks, do you perform any calibrations to determine the time constant for temperature or conductivity? That is to say, their dynamic response. Great question, James. So yes, most of our calibration is about static accuracy. It's under equilibrium. But that's because the sensor's static accuracy, or rather their static performance, is highly variable from one instrument to another, and so they must be calibrated individually. Their time constants do not typically vary significantly from instrument to instrument, depending on the sensor. So let me give you an example. With temperature, we have 3 different thermistor time constants, or rather manufacturing approaches that result in either our standard thermistor that's used on moored instruments, our fast thermistor that's used on profiling instruments, and our slow thermistor that's used often on seafloor applications where you really are not measuring temperature very often at all. And we characterize the time constant of those here by doing plunge tests from one fluid into another, typically from air over a big step change into a well-stirred fluid bath. And then we measure the time constants there. So the fast thermistor, for instance, our fastest thermistor, which is about 2 millimeters in diameter in its sheath, that has a time constant on the data sheet of less than 100 milliseconds. Its actual value is very close to 70 milliseconds, and it has about a 10% variation from instrument to instrument, so 70 plus minus 7. Likewise, our standard thermistor on the datasheet we say is less than 1 second. Its actual value is closer to 700 milliseconds, and the same kind of 10% variation over the builds. Our slow thermistor is really slow. It's usually embedded in a large, like in the pressure housing, for instance, with about a 30-second time constant. Alex, could you please rapidly go over oxygen and conductivity sensor checkup calibration possibilities in the field, which is often preferable after shipping? Sure. So oxygen, I think the easiest thing to do with oxygen is to make a measurement in air. You should get a reading that's approximately 100%. The second most or simplest is to get a little bubbler, like a fish tank bubbler or an aquarium bubbler, put that in fresh water or salt water, it doesn't matter, and put the instrument in that. That's the quickest thing to do. And of course, with the optodes, we have 3 time constants there as well. So we have our slow time constant, which is a 30-second time constant suitable for moored work. That foil on the optode is black. It's not actually black because that's the active area. That's a protective coat of Teflon. That protective coat allows it to be wiped for anti-fouling purposes, but it also makes it slower, which is why it's 30-second time constant. Our standard foil is pink. It looks like a pink Post-it note, pink sheet of paper. That has about an 8-second time constant. And then the 1-second time constant for profiling is almost translucent. It's clear with a hint of pink in it. And both the standard and the fast optodes, the pink and the translucent pink, you can see the LEDs flashing on the inside. So that's another quick check to make sure that the instrument is working. For calibration, for conductivity rather, simple immersion in salt water is all that's necessary. The instruments have no glass in them. And this means that they don't crack and get damaged. I know that if you've used glass electrode conductivity cells, many of you will be familiar with the bend test. You shouldn't do this unless you suspect it. But when a cell, for instance, goes back to seabird and it's not behaving correctly, they bend it in their hand very slightly next to their ear to hear the crunching noise of the broken glass tube. RBR's internal ceramic doesn't crack in that way. And so there isn't that same level of concern over shipping damage. The same is true, you can freeze our conductivity cell. And in fact, many people freeze it over winter. It won't measure conductivity while it's frozen, but it's not damaged at all. And come spring, you'll be measuring conductivity again quite accurately. Patrick, thank you for the tour. Well, he said wonderful, but that felt like blowing our own trumpet. How would you recommend cleaning our titanium CTD and sensors prior to returning them for annual calibration? Oh, you're a man after our own heart. Freshwater rinse. So freshwater rinse to get rid of the slime, and then a bottle brush or a scrubbing brush to get rid of anything that's particularly built up. One of the things that we often suggest to people, even in the field, is it relates to cleaning the pressure sensor. So the pressure sensors on our instruments always have a little clear guard over them. And the guard is there to stop you sticking things into the pressure sensor. The pressure sensor membrane is only about 10 microns thick. It's extremely thin, and touching it with, mentioning no names, a screwdriver is not going to work very well. Well, you're going to be able to successfully touch it, but you won't be able to successfully measure pressure after that. Sometimes that plastic cap, which has some holes through it, still gets some calcium buildup on the inside, and it doesn't seem to come off just by rinsing. The way to get it off is not to use abrasives or tools. It's simply to take a little bit of common vinegar, acetic acid. And if you put the instrument or put the end cap that has the pressure sensor, you can put the whole instrument in vinegar, it doesn't matter. But if you put the end cap in instrument, the pressure sensor, in vinegar for overnight, then you'll find out in the morning that it just rinses off. And generally, you know, if you tape the instruments, for instance, as common practice to ease in your anti-fouling, remove the tape before it comes back, just so that we don't have to do that. It's basically, if you were happy to put the instrument into a bowl of water and then drink the bowl of water, if you're happy to do that, we're happy to calibrate it in that state. Alex, could we say a few words on CH4 and CO2? So those really depend, as you can imagine, on the different sensors. Both dissolved gas sensors for methane and carbon dioxide are slightly trickier. And so rather than getting into that now, I'm going to say, I'm going to suggest if you would be able to write to our support team, they will then get your email address from that, and they'd be able to give you some guidance. That support team can be found at support@rbr-global.com. Support@rbr-global.com. Thomas Wilson, what do we use? He missed the first bit. What do we use as our primary temperature standard instrument? So we don't actually have a temperature standard instrument. We don't use an instrument to transfer the standard. We use platinum resistance thermometers, SPRTs, standardized platinum resistance thermometers. And those are calibrated in our lab, Thomas, against the triple point of water, the melting point of gallium, and the triple point of mercury, which we do ourselves. We also anneal the SPRTs, which is useful to remove drift. All platinum resistance thermometers have a little amount of drift over time, which we monitor. And as soon as they have drift that's egregious, we anneal them. That basically takes the crystal lattice and realigns it to get rid of any stress that's crept in. David Spear asks, what do you recommend for anti-fouling for moored instruments? Well, the first thing I'd say, David, is that our mission is that your deployment is successful. And so if you tell us that you're going to deploy a CTD in warm, well-lit surface waters, we would not recommend rbr CTDs, because the fouling that's going to occur there is going to be voluminous, large amounts of a high volume of seaweed and algae attached to them. And we really have almost a religious dogma against using tributyl tin, because it's a heavy metal that never ever comes out of the water column. So we recommend the use of our instruments in environments where fouling is lower. And typically it's maintained by regular servicing and cleaning. The cleaning doesn't need to be done using any special soaps. You don't need to use, for instance, Triton X or any special care. You can use a brush, a bottle brush, a scrubbing pad. The instrument is very immune to what you might call abuse, especially if you come from the electrode conductivity world. We do have some plans in place for anti-fouling measures that will be useful in environments where you have larger power supplies. But it's very difficult, you'll have seen, even in instruments which use tributyl tin, the deployment lifetimes fall off very rapidly because in order to build up that concentration, you have to add a pump and then turn the pump off to prevent any flushing. RBR instruments have the flushing occurring naturally, so you don't need any mechanical addition to ensure that the instrument gets a great measurement even on a mooring line that's relatively static. Oh, thanks, Candice, for making sure that my spelling came out correctly for the written record.
That was all the questions that are in the chat right now. I'm not going to stop the conversation, but I'm going to stop the recording. And then again, if people want to come on and say hi, that would be great. So Thank you, Greg.
Most